Hello everyone, and here we are for another review video for the dynamics test. I'm just gonna jump right in. So we've had requests to go over a problem, or several problems for the test. I'm going to do two problems in this video. Both of them are fairly involved, but if you can do these problems, then you're pretty much set to go. So the first problem I'm going to do is the problem with the apple falling out of the tree. So in case you don't remember, there's a tree with an apple in it, red apple, right? And this apple falls out of the tree into some grass on the ground and comes to a stop as a result of it hitting the ground. And the question, I believe, is what force does the grass exert on the apple to stop it? Some of the other information we have is that the apple is 2 meters above the grass, and that the apple falls 0.6 meters into the grass, I believe. 0.06, excuse me. 0.06 meters falls into the grass, 0.06 meters. So 6 centimeters when it comes to a stop. So the first thing we do, obviously, is draw a picture, which we just did. The next thing I'm going to do is I'm going to focus right now on the part where it is in the grass. So in grass, because there's several different portions to this problem. There's the portion where it is in the grass, there's the portion where it's falling through the air. So in the grass, if we draw a motion diagram for the motion of the object in the grass, we know that it fell down, is moving, and then as it hits the grass, it starts slowing down to a stop rather quickly. Given that this is the motion diagram, positive, negative, the delta V arrow is going to be right here, which means that the sum of our forces for this interaction is going to be up. Now that we have our motion diagram, we can draw a force diagram. The objects interacting with the apple as it falls into the grass are going to be the earth and the grass, obviously. Nothing else here. So if the earth is always pointing down, right, force earth on apple, and the grass is exerting a force up, and we already said that the sum of the forces up has to be bigger, or the sum of the forces has to be pointing up, so it has to be bigger in the positive direction, which this is positive y. There we go. So this is the force of the grass on apple. All right, now we have our force diagram. Now, even if you have no idea how to do the problem, okay, no idea whatsoever how to do the problem, you do know how to draw a force diagram, how to draw a motion diagram, right? You do know how to draw a picture, include all the information. One thing we know about the apple is that it has a mass of 0.1 kilogram. So it's important to know. So you know how to include all the information in the picture, you know how to draw a motion diagram, you know how to draw a force diagram. You also know, at the very least, one equation that you're going to have to use in this problem. Every single dynamics problem, pretty much every time, is going to involve the equation for Newton's second law, which is the A is equal to the sum of the forces in the direction of acceleration over the mass. In this case, we are looking for the sum of the forces in the y direction. You'll notice that in the x direction there are none. So the next step is to identify the forces that are causing our object to accelerate. We know that the forces interacting with it are the force that the grass exerts on the apple and the force that the earth exerts on the apple. And there are no other ones in the y direction, so we can just plug these in here. We know that the force that the grass exerts is positive, the force that the earth exerts is negative. So we've got force grass on apple minus force earth on apple over the mass of the apple. Now, again, I have yet to try and solve for anything, or even say that I'm going to solve for anything. I'm just taking parts of the problem and plugging them into my Newton's second law equation for use later, because we will be using this equation at some point. So now what we're trying to solve for is we're trying to solve for the force of the grass on the apple. So I'm just going to isolate that and solve for the force of the grass on the apple. Force grass on apple, I'll multiply both sides by m, resulting in ma here, and then I'll add force earth to get it by itself. So we've got a acceleration in the y direction times the mass of the apple plus force that the Earth exerts on the apple. We also know there's an equation for the force that Earth exerts on an apple. So unless we're given that force already, we have to use an equation to figure out what this is. This is A times F times the mass of the apple, plus the force that Earth exerts on anything, which we know is mg, right? This is mass of the apple times our good friend g. All right, now this equation's all well and good, and this will give us the force that the grass exerts on the apple. But there's one piece of information missing, right? We do not know what this acceleration is. So it's at this point that you would probably think, oh, well, clearly I forgot to give you some information, or, well, I can't do the problem. But remember that the problem involved two other bits of information, that the apple sunk into the grass by 0.06 meters, and that it started 2 meters up. So effectively what's going to happen, if we draw now the motion diagram for our whole interaction, is that you first have the apple accelerating down, right, because it ends up in free fall due to the force that the Earth exerts on it, right? It's going to end up at some velocity. It starts off v initial equals 0 at the very, very beginning, and it reaches some v final, right? This v final is going to be our v initial here, right? Right when it hits the ground, we have this v final, which then results in v equals 0 again. Of course, our delta v here is this way. So what we can do is we can use the fact that it starts off at v equals 0 meters per second, ends up at some v final. This v final gives us some v initial here, sorry. This v final is going to be our v initial for while it is in the grass, and that v initial ends up as 0 again while it's in the grass. So here there is some acceleration, and therefore we can find out what the velocity is, and here there's some acceleration, or so here there's some initial velocity, which can allow us to find this acceleration, which is the acceleration we need here. Okay? So again, it falls out of the tree 2 meters. We can use that information to find the final velocity here right when it hits the grass. This final velocity will be our initial velocity while it is in the grass. And given that we know how far it sinks into the grass, the initial velocity, once we find it, and the final velocity being 0, we can find out what our acceleration is that we need to plug in here to find out what the force of the grass on the apple is. So, let's do that. So, in the air, or in, I guess, while it's falling out of the tree, maybe rather than in air, because it's in the air the whole time, isn't it? So, out of tree. Alright, so we know that it falls 2 meters, so I'm going to say that delta x is equal to 2 meters, and we know that v initial is 0, and we are looking for v final. We don't have any time here, and we don't, well, oh, there is one more piece of information. We know while it's falling out of the tree, we know that the acceleration is equal to g. So we have acceleration, we have displacement, and we have our initial velocity. We're looking for final velocity. We are not given time in this problem. Could we find and could we solve for the time? Sure we could. But since we are timeless, we might as well use the timeless equation to solve this. So our timeless equation, if you recall, is that v final squared is equal to v initial squared plus 2a times delta x. You'll notice we have our v final, or we're looking for v final. We have v initial, we have a, and we have delta x. Let's just keep in mind that in this scenario specifically, our a has to be negative because it is falling down. It starts off at 0 and ends up with some final velocity, which is going to be negative. So plugging this stuff in, we've got our v final squared is equal to v initial, which is 0, plus 2 times a, which is negative 9.8 meters per second squared, times delta x, which is actually negative 2 meters. 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 2 which is actually negative 2 meters. The reason it's negative 2 meters is because we're saying that up is the positive direction and down is the negative direction. So we end up with 0 from here going down minus 2 meters for our displacement. This will also ensure that when we take the square root over here, we don't end up with a negative number over here, right? So, so we can now do v final is equal to the square root of 2 times negative 9.8 meters per second squared times negative 2 meters, which gives us a final velocity of 6.26 meters per second. And of course this velocity is negative because it is downward. Remember, when you take a square root, it's either plus or minus. In this case, it's minus. All right, now that we have our final velocity here, this final velocity is going to become our initial velocity when we look at it while it's in the grass. So we now know that our initial velocity while it's in the grass is negative 6.26 meters per second. We know that our final velocity equals 0 meters per second. And we know that our displacement in the grass is going to be 0.06 meters. Again, negative because it is falling down into the grass. So we once again are not, and we're also looking for A. Now, once again, we are not given time in this part. So obviously we need to use, once again, the timeless equation. Only this time we're going to use the timeless equation and solve for A, because that's what we're looking for. So again, our timeless equation, squared is equal to v initial squared plus 2a delta x. Solving for A is equal to v final squared minus v initial squared all over 2 delta x. So plugging in, v final is 0 minus our v initial, which is going to be 6.26 meters per second, negative 6.26 meters per second, squared, over 2 times our delta x, which is negative 0.06 meters. So going through all that, plugging that into your calculator, you find that the acceleration was a rather large 326.7 meters per second squared, which is pretty crazy. So that is our acceleration. Now, this acceleration is what we plug in here to find the force that the grass exerts on the object, or on the apple, excuse me. So we can plug in this information here. Acceleration is 326.7 per second squared times the mass of the apple, which is 0.1 kilogram, of course, plus the mass of the apple times g, so 0.1 kilogram times 9.8 meters per second squared. Could you have factored out the mass here and just had a plus g? Sure you could. This will give us a final force of 31.7 newtons that the grass exerts on the apple. All right, so that's that. This is a longer problem that I would normally do on a test. If anything, I would ask you for these 3 bits of information separately. So like, for example, this would be part A to find the velocity right before it hits the grass. This would be part B to find the acceleration in the grass, and this would be part C. But it's good to be able to do a big problem like this, especially in preparation for the AP. All right, so the second problem I'm going to do is not one that you've seen before, really. It is similar to the quiz that I gave with the two-body problem, but I've added sort of an extra exciting part to it to make it a little bit more challenging and to also incorporate friction into the problem. So a person is pulling 2 crates across a frictionless portion of the floor. The whole system is moving with an acceleration of 0.75 meters per second squared. The mass of the box the person is pulling is 5 kilograms, and the mass of the second box is 8 kilograms. The question is asking what is the force the person is pulling the first box with, and what is the tension in the rope connecting the two boxes. All right, so just to draw a picture, I'm not going to solve this yet, but just to draw a picture of what's happening. So you've got your two boxes. This is the 8 kilogram box connected with a rope to another box, which is only 5 kilograms, and a person is pulling those two boxes across a non-friction floor. Obviously not a straight floor either. Then sometime later, at some point, the man pulls the boxes onto a part of the floor that is not frictionless anymore. All right, I'm gonna work a little magic here. So now the same guy is pulling, but this time the floor is not frictionless. There is some friction between the boxes and the floor. And the coefficient of friction between the boxes and the floor, mu, is equal to 0.25. All right, and then the question is, what is the new acceleration of the system if the man keeps pulling with the same force that he was pulling here, which we've got to find at some point. And then what is the tension in the string connecting the two boxes this time? So before, what is the tension in the rope connecting the two boxes? You found that before, now you'd have to find it again. So at this point, what I would like for you to do, rather than listen to me solve the whole problem by myself, I want you to try it first, since you haven't actually solved this problem yet. Do whatever you need to do to solve the problem, and then when you're done, come back. So pause the video, then come back and check the solution with me. I'm going to give you a chance to do it now. No, seriously, like actually pause the video and do the problem yourself. It's okay, I can wait. Okay, well, if you haven't done it by now, you are robbing yourself of an opportunity to do some real learning, but if I can't guilt you into it, then I might as well just go ahead, because I don't have forever here. So, let's start. As with any problem, after you've drawn the picture, you can draw a motion diagram, just to be sure that you know what direction the sum of the forces is in. So, if our system, I'm going to take our system to be both boxes for the motion diagram, since they are going to have the same motion diagram, and we know that the system, as it says in the problem, is accelerating, so our arrows are going to be getting bigger, and they're accelerating this way. Whoa, delta V, what just happened? Sorry. And we'll say that this is the positive direction. Now here, I'm not quite sure what's going to happen. I haven't actually done the problem myself yet, but it's possible that the motion diagram could not necessarily be this over here, but we'll find that out later. Now, the force diagram resulting from this motion diagram, I'm going to now split that up into two different ones. I'm going to do the force diagram for the 8 kilogram blocks in red, and I'm going to do the work or the force diagram for the 5 kilogram blocks in green. So the 8 kilogram box, since it is accelerating to the right, it has a net force going this way for the force that the rope exerts on the box, otherwise known as tension, right? Tension rope on box. And then we also have, obviously, the force that the floor exerts on the box, right? And here we have the force that the earth exerts on the box. Now keep in mind, this force floor is also known as the normal force, or this is also known as the perpendicular force on the floor, on the box. The perpendicular force of the floor on the box, excuse me. This is also known as the normal force. Now for the 5 kilogram blocks, we have a slightly different force diagram. We've got still the force that the floor, perpendicular force that the floor exerts on the box. This is the 5 kilogram blocks. And here is the force that the earth exerts on the box. We've got the force that the rope exerts on the box, or that the person, rather, exerts on the box. And we also have, pointing in this direction, the same size as the other one. We've got the same size as this one. We've got the force that the rope exerts on this box. Okay, so let's call this, I don't know, box 1, and we'll call this box 2. So this would be on box 2. And then this will be box 1. There we go. And notice that this arrow should be bigger than this one because the whole system is accelerating to the right, so this arrow obviously has to be bigger. Now, there is another way to solve this first part of the problem, A, what is the force the person is pulling with the box, by realizing that since these two things are connected, you can count them in the same system. You can count them as being part of the same system, or both the same, one system rather. So you could just add their masses together and treat it as if it was one big 13 kilogram box, and then find the acceleration that way. I'm not going to do it that way because this way allows us to essentially find both of these at the same time. And let me show you how. So, doing Newton's second law, now that we've drawn our force diagrams, like I said, we'll do Newton's second law for each one. So we've got the acceleration for box 2, which we know is the same acceleration for box 1, is equal to the sum of the forces exerted on box 2 over the mass of box 2. For box 2, the only object that's causing it to accelerate in the x direction is just the force of the rope, or the tension rope on box 2 over the mass of box 2. Now, doing this, you realize that we've actually just found the equation for what is the tension of the rope connecting the two boxes, because we know that the acceleration is 0.75 meters per second squared, and we know that the mass is 8 kilograms. So if we do tension rope on 2 is equal to A times M2, we get 0.75 meters per second squared times the mass, which is 8 kilograms, which gives us a force of 6 newtons, or a tension of 6 newtons on the rope between the two. Now, let's go to this one and do the Newton's second law for this one. So I'm going to do this over here. A is equal to the same thing, sum of the forces, now on box 1, right, in the x direction, over the mass of box 1. Now the sum of the forces exerted on 1 are the force of the person on box 1, minus, since this is the negative direction, right, make this positive, this negative, this positive to the right and up, and negative to the left and down, minus force rope on box 1, or the tension on box 1, or the mass 1 tension. There we go. And so now we want to solve for this one, for the force that the person exerts, since that's what we're trying to find. So we've got AX times M1 is equal to force person on box 1 minus tension rope on box 1. And then solving for force person on box 1 is equal to AX times 1 plus tension. Now we can just plug in. We already know that this is 6. We know what the acceleration is. We know what the mass is. So we've got 0.75 meters per second squared times the mass, which is 5 kilograms, plus our tension here, which is 6 newtons, which will give us a final acceleration, will give us a final force, excuse me, of 9.75 newtons. Great. So the guy's pulling with a force of 9.75 newtons. The rope is exerting a force of 6 newtons on between the two boxes, on pulling this way on box 2 and pulling to the left on box 1. Alright, now let's do the second part of the problem, because that's the exciting part. So now things are slightly different. We have a similar situation, except the guy is still pulling with the same force as it was before, but now we are on a surface that has a friction, between the two surfaces of the boxes and the floor, and it has a coefficient of friction of 0.25. So the question now is, what is the new acceleration of the system if the man keeps pulling with the same force? And what is the tension in the string connecting the two boxes this time? So what I'm going to do is I'm going to copy over the force diagrams and just make some slight changes to them. Alright, that wasn't so bad. So now, our force diagrams are going to be slightly different now, right? So in the case of this one, we now have another force arrow going this way. Everything is the same. Now we have another force arrow, however, which is the friction force. In this case, obviously, since the boxes are sliding, this is kinetic friction. And here, on the other one, we also have yet another force, which is the kinetic friction force on this one. Okay, so this is kinetic friction on, wrong color, on 2, and here we have the kinetic friction force on box 1. Alright, so now let's set up our equations once again. For box 2, we now have, instead of just the tension in the rope, we've got this new tension rope on 2 minus force friction kinetic on 2 over mass of 2 is equal to our new acceleration, right? And then for the green one, or for the first box, we have the same forces as before, force person on 1 minus now the tension on 1 minus the friction force kinetic on 1 over the mass. It's equal to our acceleration. So we need to find a way to be able to solve for our acceleration and the tension force. So we're going to do this in two parts. We're first going to do the acceleration, and then we'll do the tension. So in order to solve this, we have to get as many like terms onto one side, and then which will allow us to sort of solve this system of equations. Since we want to solve for acceleration, or since we want to find out what the acceleration is, I'm not going to set these two parts equal to each other. What I'm going to do is I'm going to solve for the tension, because the tension is the same in both of them. So I'm going to solve for the tension first, and then set those two equations equal to each other. So, solving for the tension in both, we get A times M2 plus force friction kinetic on 2. This is going to be equal to the tension rope on 2. And then solving for tension in 1, we get tension on 1 is equal to force friction kinetic on 1 minus we get force person on 1 minus A times M1 minus force friction kinetic on 1. If you're not sure how that is, just go through the steps of isolating the tension. Okay. So now we can set these two equations equal to each other because we know that the tension on 2 and the tension on 1 in the string and the rope are both the same. So we now have AM2, and no, I'm going to switch to black for this. So we now have AM2 plus force friction kinetic on 2 is equal to force person on 1 minus AM1 minus force friction kinetic on 1. So remember, we're solving for acceleration here because we're trying to find the acceleration. So I'm going to put the acceleration term over on this side. And so we have, and move everything else to the other side. So we've got A, and I'm going to factor out the A's. M2 plus M1 is equal to force person on 1 minus force friction on 1 minus force friction on 2. Alright, so, and then dividing by M1 plus M2, we get just the acceleration. But I want to save room. So we know what the force that the person is exerting. It's this one from before because it's pulling with the same force. But we don't know what these are. But we do, however, have equations to solve for these, right? If you look in your equation sheet, we know that the friction force is equal to mu times F normal. And in the case of this problem, the normal force in each one is always just equal to the force that the Earth exerts, right? Because the forces are balanced in the y direction. So the normal force on either box is equal to the force that the Earth exerts on that box. So in this case, this is equal to mu mg. So the mu times the mass of the box times g. So I'm going to substitute that equation in for our friction force parts, or our friction force components. So we got force person on 1 minus mu m1 g minus mu m2 g all over m1 plus m2. This is going to give us, this is going to give us our acceleration. And now it's just a matter of plugging everything in. Or plugging in to find our acceleration. We get negative 1.7 meters per second squared. Now, you may be asking yourself, did I get this wrong? How could I get a negative acceleration? Well, think about it. If you were moving in the positive direction before, right, he was pulling it this way, and then there was this new friction force. If it was moving initially to the right, and now there's an acceleration in the negative direction, what is happening? Okay, that's right. It is actually slowing down. So it was moving to the right, but now, which is why I didn't draw the motion diagram before, because our acceleration is no longer causing it to go faster, but is actually slowing it down, resulting in acceleration in the negative direction. Okay, cool turnout. From here, we can find what is the tension in the string connecting the two boxes, because it's as simple as plugging our acceleration into either one of these equations that we had before, right? And just solving for this. So let's do it for this one since it's shorter, okay? We know that our tension rope on 2 is equal to A times M2, now that we know A, plus force kinetic friction on 2, which we know is mu m2g, which, if you plug this in, gives us a force or a tension of, believe it or not, 6 newtons. Interesting how that works, huh? Alright, there you have it. So again, just to reiterate some good steps for solving these problems. So step 1, so problem solving strategy, and I did give you this problem solving strategy already, but take a look at it again. Step 1 obviously is draw a picture. 2, obviously draw diagrams, either motion or force diagrams, whatever you need. And even if you think you have no idea how to do the problem, this is always a good place to start. Don't think about where you need to end up, just think about what you know and go from there, okay? Don't stress out immediately if you think you don't know how to do a problem. Going through these steps might allow you to realize that you actually do know how to do the problem. Once you draw the diagrams, write out Newton's second law. And once you have Newton's second law, start subbing in known equations. What do I mean? So when you have the sum of the forces, right? You plug in, you start putting in all the forces that cause acceleration. When you see force friction of whatever kind, you know to plug in the friction force, which is mu times F normal. From here, when you have the normal force, you want to plug in the equation for, whatever force the surface is exerting. So whatever is balancing out the downward force, okay? If you have force Earth on object, you automatically want to plug in mg, right? So just substituting in known forces or known equations as you go through the problem. Then what I would do from here is algebraically solve for desired value. Their desired variable. Alright, and then plug in. If you see that you're missing some variables, go back and try and find another way to find the variables you're missing. If you have a two-body problem in a system of equations, solve for a variable that's the same on both sides, set them equal to each other, and go from there. Alright, I hope this was helpful. Please let me know if you have any questions, and I'll see you on Monday.